Hello, everyone. I hope you're all having a lovely afternoon despite the looming exams. And welcome to what is sadly the final NPPS seminar of the year. Before we start, I just want to say thank you all for coming. Again, I know you are all very busy. And also to give a special thank you to everyone who has come to quite a few of these throughout the year. So you've all played a massive part in making these seminars as successful as they have been. And we really couldn't be more grateful. So we thought we'd finish with something really special, and we're very excited to be joined by Professor Heather Gray from the prestigious UC Berkeley, all the way in California. So Professor Gray is currently an assistant professor specializing in particle physics at Berkeley, and her enviable career has seen her conducting research at CERN, as well as the Lawrence Berkeley National Laboratory, which is the lab at Berkeley. Since joining the ATLAS collaboration in 2006, Professor Gray has made significant contributions to the ATLAS experiment, culminating in her strong role in the searches and initial measurements of the Higgs boson interactions with quarks. For this, she was awarded the IUPAP Young Scientist Prize in 2018. So our seminar today will further explore the Higgs and really why its discovery in 2012 was as groundbreaking as it was. So without further ado, I'll hand over to Professor Gray.
All right. Hi, Jonathan. Thank you so much for inviting me to join everyone today. And yeah, thanks to everyone for taking the time out. I hope this will give you a little bit of light relief for the examinations. So before I get started, just a heads up, I love questions. So if anyone has a question, feel free to interrupt me or drop them in the chat. Also totally fine if we have questions at the end. All right, so what I'm going to tell you today is about something called the Higgs boson, which some of you may have heard of, some you may not. And this is something that we like to think of as the final piece of the Standard Model. And so during the first bit of the talk, let me unpack that a bit and kind of tell you why. So let me make sure that I share the slides. Can you see the slides? Everyone happy? All right. So there we go, Higgs boson, the final piece of the Standard Model. So before I get started, we can do this quickly. Just wanted to say a couple words about who I am. So as Jonathan was saying, I'm an assistant professor here at UC Berkeley. I'm also a faculty scientist at Berkeley Lab. And what I do is I really study the Higgs boson as a member of the ATLAS experiment at CERN. And so here's a picture of me a couple years ago, really inside the detector cabin at CERN. And that experiment that you can kind of see on the right here, that is really ATLAS itself. So you may be noticing I have a bit of an accent. Maybe if you're paying close attention, you'll be noticing that I don't sound entirely American. That's because I'm not. I actually come from South Africa, did my undergraduate at Cape Town. Then I did my PhD, flew across the world to America, did my PhD at CalTech, but actually spent most of my time in Geneva, in Switzerland, working at CERN. After that, I moved first to Berkeley Lab and then to UC Berkeley. And always when I look at the slide, I kind of think that maybe I choose my places where I work by how pretty they are. At least I've been very lucky to actually have all the places where I've been to being really beautiful places. So let's move on to sort of one of the stars of the show today. This used to be the view that I would see pretty often when I was flying into Geneva in Switzerland. And so what you can see here is you can really see Geneva Airport that's kind of hiding back by between this big ring and the lake. So you may be asking, what's this big ring? Of course, that's the Large Hadron Collider. And it's not quite what you see when you go to CERN, because indeed the Large Hadron Collider is actually about 100 meters underground. It's a gigantic accelerator ring, 27 kilometers, and really nestling across the border between France and Switzerland. The border, that's that sort of white dotted line where you can actually see between the two. So what is the LHC? Kind of one way to think about it is that it's a really large, a gigantic microscope, okay? And what I mean by that is if any of you have heard about the uncertainty principle, this is the one, right, where you can kind of relate things that you know about distance to things that you know about momentum. What that actually means is that if you have particles that can go up to really, really high momentum, it actually allows us to be able to probe very small distances. And so that's kind of what I mean by a microscope. You'll see why I'm interested in a minute about like probing these small distances. But essentially, the higher energy I can make this accelerator, the smaller the distances that I can go to. So in particle physics, we use some weird units. And we call something which is called tera electron volts. And so the energy in this Large Hadron Collider, or the LHC, is 7 TeV. But putting it into more everyday terms, that's something like 0.9999999 times the speed of light. Of course, that's not really everyday units. What it actually means is that for all practical purposes, the protons go essentially at the speed of light. So what am I actually after here? And so in order to do that, I kind of want to start by more everyday objects, things like atoms, which we're all made of. So here's a nice little sketch where you can see an atom, and you can also see the approximate size of an atom, something like 10 to the minus 8 centimeters. And in particle physics, we actually like to always ask the question, what are things made of? So you might ask, what is an atom made of? And if you ask that question, you're able to look with a smaller and smaller distance, so with a more powerful microscope, you can actually find that it's made of a nucleus and some electrons orbiting the nucleus. The nucleus is actually way smaller than the atom, right? It's 10 to the minus 12 centimeters. And the electrons, we don't actually know how big they are. We know that they're less than 10 to the minus 16. In fact, we suspect that they might actually be point-like, i.e. have no size whatsoever. Then you might ask for the nucleus, what's inside the nucleus? And if you're able to look inside, you can see that it's made of protons and neutrons. Then, getting an even more powerful microscope, you can actually ask what's inside protons and neutrons. And what you'll find is that inside them are actually quarks. And that's where we are right now. We think that quarks and electrons are fundamental particles. And what we mean by that is there's nothing inside them, but we don't actually know. And so that's one of the things I love, is it's pretty easy to come to these questions, which are pretty big, and we just have no idea. And that's why things are exciting. But what we have now is something called the standard model. And this is actually a sketch of that standard model showing you all the different particles that are inside it. I kind of like this one because it has a sort of circular view where you put the Higgs boson right at the center. And you can kind of see the quarks, all the different quarks. You can see the forces, you can see the leptons. You'll see actually a different picture of it in a second. But the reason I like this one, and the reason I wanted to mention it, is because there's a movie called Particle Fever, which is pretty cool. I recommend it. And this is about the discovery of the Higgs boson at CERN. I have about a 5-second cameo in that film, so I'm pretty proud of that. That's my entirety of my movie career history. But nonetheless, I think it's a pretty good movie, and it gives you a good feeling for, what it was really like at that time with the discovery of the Higgs. This is another picture. Here you can see that I'm doing lots of, and sorry, what I forgot to mention, that diagram that I just showed you, that was actually made by the directors of the film. So I was kind of amused that I actually enjoy this diagram, which was movie producers who ended up making it rather than necessarily physicists. Oops, okay. So back to the standard model in another view, and this one is particularly silly. This is a company called Particlezoonet. They actually make these soft toys of all the different particles in the standard model. I own the Higgs boson, for example, to do it, but you can buy the whole collection if one wants. And here you can see the same particles I was showing you, arranged into these quarks, and these actually make up all the matter that we have. Then we have the leptons. These are also part of matter. And there you have kind of two types. You have the electron, the muon, the tau, and also the neutrinos. These are sort of massless ephemeral particles. And then we have the forces, which you can see on the right to do it. And I've highlighted a few of them because they're going to kind of come up later on in the talk. Of course, the Higgs boson is the star of the show, but also the photon, also the electrons and the muons. These are actually going to come up again. One thing you may be noticing is that there are a lot of particles in the standard model, right? This is meant to be what everything's made of. Seems awfully complicated. That's true. And that's one of the things why people are not sure if this is really the final answer, if this is really going to be the theory that actually defines everything that we know. One example here is the fact you can see that there are all these labels that are 1, 2, and 3. These are actually different generations of particles. So you have, and they're actually effectively copies. So you have like 2 particles, and then you have the second generation, it's copy of the first, exactly the same, just a bit heavier. And people don't know why. We don't have a good theoretical reason. We just know that it is that way to do it. So yeah, you can sort of see this, and you can also see why many physicists are not sure that this is really the final answer. So then, because protons are going to come up a lot in the LHC, I wanted to tell you what a proton is made of. It's actually made by combining these building blocks together. And here, what we're going to need are the up quark and the down quark. And if you want to make a proton, it's made of 2 up quarks and 1 down quark. Whereas if you have a neutron, that's actually made of 1 up quark and 2 down quarks. And you can imagine that this is how you might go and make a whole bunch of different particles by combining these building blocks in various different ways. So now we've talked a bit about the particles. Let's talk now about how we're going to collide them. And so this is a little sketch telling you what's going on. On the next slide, there should be a movie that I'll play for you. And in the LHC, we have 2 beams of protons, and they're called the red beam and the blue beam, and they just circulate in opposite directions. One of the beams goes clockwise, one of the beam goes anti-clockwise. And those colors, that's really how they're called. So if you sit in the control room, you'll see, red beam's coming, blue beam has a problem, that sort of thing. Then within these beams, what we have is we have bunches of protons. The reason for this is it's actually pretty hard to take 2 protons, aim them, and make them collide. So if you instead have large bunches, something like 10 to the 9, then you have a way better chance of getting any 2 protons to collide. And so that's why we have bunches. And what we do is we actually distribute them regularly all the way around the accelerator. Then we organize things that they will actually collide. And what really happens is you have like 2 protons, 1 from each beam, that will actually collide. And in fact, it's within those protons, which are mostly open space, it's the individual quarks or gluons that actually will collide. And what we're trying to do is we're trying to destroy them. We want those quarks and gluons just to be collide together, to be completely destroyed, converted into energy using A equals mc squared, because that allows us to actually produce new and interesting particles that would later on decay, and that's really kind of what we're after. So here's a little movie where you can actually see what happens where 2 bunches of protons are ejected into the accelerator chain of the LHC. You notice that you have these big rings. Each ring, we're actually able to accelerate them up to higher and higher energies. Basically, as you make it bigger, it's easier. And now they've entered into the LHC. They're kind of rotating around, getting up to high energy. Now we're going to kind of dive inside the LHC. You can see the dipole magnets, note the graffiti on the right. And now we're really following along the accelerator with that bunch as it's going around and getting up to higher and higher energy. You can see the nice quarks bouncing on inside the proton. And then what we notice is up ahead comes an experimental cavern. And we've timed things that these 2 bunches are going to meet at the center of this is the Atlas experiment. You notice they're colliding, getting destroyed, and they're producing a whole bunch of particles. You can see the pieces in the detector are lighting up as the particles go through. And that would be how we would actually see the event. Of course, I've chosen an interesting event here. This is actually a Higgs boson decay, which we'll come back to a little bit later. So how big is the LHC? I said it's big. So I thought it was easier to get the scale is to move it to Manchester. So there's a fun little app where you can move the LHC wherever you like. So I moved it to Manchester. It's pretty big. I guess it takes out a chunk of the city and perhaps maybe what you consider not quite part of Manchester. You can tell me a little bit later. And so that's the real Large Hadron Collider, as we said, in Geneva. Now, we don't just need a collider. We also need these detectors to actually be able to measure the particles that are produced in the proton-proton collisions. And at the LHC, there are 4 main detectors, but there are kind of 2 that are most relevant for our story today. There is Atlas, which is my experiment that I work on. And then we have a competitor right on the other side of the ring, which is called CMS. Now, the reason that there are two of them is because doing these particle physics experiments is very, very hard. We're looking for incredibly rare processes. And you're not able to build many accelerators. They're extremely expensive. And so the idea is to have two independent experiments so that we can actually cross-check each other's results, because it's extremely unlikely that if one of us makes a mistake, that if the other experiment is truly independent, that they would actually make the same mistake. And so that's why we have these two, and we're kind of sort of loose competitors. I mean, I have plenty of friends at CMS, but indeed we actually keep our experimental results confidential until they've been approved by the collaboration and they've become public. So here's a picture of the Atlas and CMS detectors. And if you're paying attention, I hope you're laughing right now, at least quietly. Of course, those are not. Those are actually Lego models of Atlas and CMS. These are the real ones. You can actually, if you look online, you can actually find various kits if you want to go build your own Atlas and CMS to do it. But here are the real ones. And if you look carefully, you can notice there are a couple people kind of hiding there. And this gives you a bit of a sense of scale. The bottom, I have some basic parameters about them. Maybe the simplest way to remember them is that Atlas is the big one. It is 45 meters long, 21 meters high, and CMS is the heavy one. It is 12,000 tons, whereas Atlas is 7,000 tons to do it. And what you can mostly see here for Atlas, you're actually seeing some of the magnet system here. And in CMS, I believe you're seeing one of the end caps. So these are some pieces on the side of the detector that you will actually have. Now I have another video, which is going to show you a little bit like what happens inside Atlas as various different particles go through. So remember, I talked right at the beginning, I talked about electrons and muons and photons and protons and neutrons. You're going to kind of see as we go through what each of those particles do. And what we're seeing is really a slice through the middle of the detector. And you can see each of these, it's a bit like an onion. We have a bunch of layers. So in the middle, we have the tracking detectors. We have an electromagnetic calorimeter, hadronic calorimeter, and muon spectrometer. And what you want to watch out for is the fact that different particles will actually deposit energy in different detectors. And that's kind of how we figure things out. So what you can see here is an electron going through and leaving a track in the tracking detector and energy in the calorimeter. Then you can actually see a photon, which goes through. And the photon doesn't leave any track, but deposits energy. And so this is actually how we would tell the difference. So I would go through an event. I would say, I have a good energy deposit in my electromagnetic calorimeter, and ask the question, do I have a track or do I not? If I do have a track, I would say this is an electron. If I don't, then I would have a photon. Now you can see a different particle going through, again, leaving a track, but it's going all the way to the hadronic calorimeter. That one is a proton to do it. Similarly, neutron, no track, nice energy deposit in the hadron calorimeter. And so that's how you could tell the difference. Finally, well, not quite finally, this is a muon, which leaves the track, goes all the way through. Muons don't interact much, so they can go all the way through to the muon spectrometers. And neutrinos, those nasty ones, they kind of don't leave any track at all. So the way that we actually see them is we need to use conservation of energy to be able to detect how much energy they had. If you're interested about that, ask me about that one at the end of the talk. All right, so that's a bit about how we do things. And maybe we can come back now into why. So the standard model itself has been really extremely successful. At the same time, as I tried to point out while I was introducing things, we also have a number of open questions. One of them, which we do know the answer to now, but we didn't know at the start of the LHC, is really what is the origin of particle masses? What actually gives these particles all their masses? Then if we look at the universe, we notice that we have this huge amount, it's actually mostly dark matter. Did you see any dark matter particles in my standard model? Nope, no dark matter particles. We have no idea what that is. Similarly, we look at the universe and we ask, why is there so much more matter than antimatter in the universe? In fact, the universe seems to be almost entirely matter. But if we look at the equations of physics, we rarely look at the equations of the standard model, we actually see that it should be about the same amount. So that's really weird. There also, another way of thinking about the LHC is it's kind of a time machine, but unfortunately I don't mean it in the useful way. It's not like you can go back to last week and restudy for your exams. Rather what I mean is that we're looking at how particles were in the universe at a very, very early stage. And that's what you can see on the right here. There's the Big Bang. There is this perhaps inflationary period. And then the LHC is probing what was going on in the universe at something like 10 to the minus 10 seconds. And there's lots of uncertainty, kind of what happened at this very early phase of the universe. Are these all the forces? Standard model has 4, if you noticed in the diagram. Maybe there are more. And so these are the sort of questions that we really want to answer with the LHC. And one of the things that's really cool is that you can try to answer many different questions with the LHC. It's really flexible in that way. Now, it turns out that back in the day, the standard model equations would actually work perfectly if all particles were massless. If anyone's paying attention, this guy is of course not really massless, right? To do it, but it feels for him like he's massless. And this is simply not true. And we know this because as experimentalists, we've actually done measurements. And I wanted to show you one of the measurements here. I'm going to show you a few plots in this talk. This is actually a measurement of the mass of the W boson, one of the particles in the standard model. And all you want to look for is you want to look at the x-axis where you can see the values for the measurement. And what you can notice is this is very far from 0. It's actually 80,000 MeV to do it. And these are a bunch of different measurements that we've actually made from different experiments. So we know it's in fact not just has some mass, it has lots of mass. And this is actually true from other particles, for example, also the Z boson to do it. Indeed, many of the particles have mass in the standard model. These are 2 ways to kind of look at it. On the left, there's a sketch. This is for those different quarks. Didn't tell you all the names. I told you about the up and down. The rest of them have weird names. There's the charm, the strange, the top, and the bottom. And basically, the size of the circle is proportional to the mass. So what you can see here is that the up and the down, which are hiding inside the protons, those are pretty light. But we have these other quarks, which are way heavier, all the way up to the top quark. This is the same thing on the right. This is actually just plotting on the x-axis the masses of various different particles in the standard model to do it. Now, it turns out that the Higgs boson is actually basically a mathematical trick. And it's really funny because it's about half a page of math. And it's not particularly complex math. Unfortunately, you need about a year of field theory before you can do see the actual details of this mathematical trick. So I'm going to just explain this a little bit conceptually. What you have to do here is we need to go into a phase space, which is using complex numbers, doesn't really matter. But at the same time, we want to just think about potentials, right? So just like potential energy, like you might have seen in electromagnetism or in other courses. And for the Higgs boson, what we need to do is we want it to be in the early universe. We want it to have this symmetric potential in the space. So you can think about it as sort of a bowl type shape. And this basically means that if you imagine you're sitting in a bowl and it needs to go to the minimum, it's going to sit there right at the center. Instead, if you can actually have this potential, which today has this weird shape, which people sometimes like to call a Mexican hat because it has this piece in the middle that sticks up. Now you imagine being this little ball and it needs to go down to the minimum. The problem here is that due to the shape of this potential, there isn't just one spot where it lands, right? If I ask you, where's it going to land? We don't know, right? It could be any of the points around the ring. And what that's actually done, this is the nature of the trick, it actually means that we've broken the symmetry of the system. If you look at the system on the right, it's perfectly symmetric, right? You know, you could flip it, you could rotate it, it's always going to be the same. If you think about the system on the right, we break the symmetry when we go down to the minimum because we choose one particular point to do it. And that's actually, weirdly enough, this is really how the Higgs mechanism works. And it sort of allows us to simultaneously have equations where the particles could behave as if they were massless, like on the left, but actually really have mass using the mechanism on the right. to do it. And that was just a sketch reminding about particle energy. So the way it works is that a particle's mass is determined by how strongly it interacts with the Higgs field. So what that means is that the heavier particles, they really interact more strongly, or particles that interact more strongly become heavier. We actually don't know which way around it is. It could be either way around to do it. So that's the Higgs boson, but it's actually a particle. And to know if it's real, what we needed to do is to try and see it. In fact, it's a highly unstable elementary particle. It has a tiny lifetime of 1.6 times 10 to the minus 22 seconds. So I can't, collect a box and show you the box of the Higgs bosons. Nope, not possible. It's gone almost immediately. So the way we need to see the Higgs is by really studying the particles it produces when it decays. And that's where those detectors that I was telling you about really come in. Now, the Higgs can decay in a whole bunch of different ways. That's what this pie chart is showing you. Most often, it will decay to bottom quarks, but it can also decay to W bosons, to gluons, charm quarks, Z bosons, etc. In fact, what the equations tell us is that the Higgs has to decay to any particle that has mass, and largely this decay is actually proportional to the mass of the different particles that we have. Now, here's a plot which is going to actually show you what happened when we discovered the Higgs boson, but let me explain the plot a little bit before I show you. So what you're going to see is we're looking here for the decay of the Higgs to a pair of photons. And in fact, if we go back a slide, you can't even see it on my pie chart. That's because it's really, really rare. But it turns out it's a good channel to look for the Higgs because the background here is really quite low. And the way that we look for this is that we take the two photons and we ask the question, what would have been the mass of the particle that they decayed from? And then we put that in a plot. And you're going to see data. You're also going to see a prediction for the background. And what's going to happen once I play the movie is you're going to see how the plot actually evolved as data came in. And so you want to keep track, you can see the date at the top right. That's really going to show you in real time. So now it starts to play, and you'll notice you see the data, it's got all these little fluctuations going on. And you want to start looking at it carefully. Can you spot any peak? Any peak coming here as we get more and more data, as we get towards the end of the year, and you notice, yes, there is a peak. Now we're done, we actually run this bit where you can actually see, and that's really where you see the Higgs boson. And indeed, you can check the mass. It's 125 GeV to do it. And this was really what happened. Now let me play the movie one more time. And I want you to ask yourself seriously the question, at what point are you confident that you've seen a new particle? It's not just fluctuations going on, because that was really the question we had to answer when we were really watching this data come in from the LHD. Is it now? Definitely not for me. Could it be perhaps now? Or do you want to really go all the way to the end of the data set? And this is actually one of the things we have to think about in science, because we do want to make discoveries, especially when they're real. But at the same time, we also want to make sure we don't think we've discovered something when actually we really haven't. Now, there's another way that the Higgs boson can decay. This was the second way that was part of the discovery. It's when the Higgs decays to 2 Z bosons, and then they decay to 4 leptons. So those would be those electrons and muons that we were talking about. And it's the same thing as before. The shape is quite different here. It's not as smooth. And so you can see in red our predictions from simulation. And now you want to play the same game and look for the peak. Hint, the scale of this plot is a bit different, but you should be able to see the peak now. And you can notice that here, it's way easier to notice the peak to do it. There are far fewer events, but at the same time, there is much more signal compared to the background. And so this is actually, now we zoom in, we do a little fit to it, and you can really see where the Higgs peak actually is. So this discovery was announced at a seminar on the 4th of July, 2012. So I like to joke and call it Higgs Independence Day. Of course, that's wrong. It was Higgs Dependence Day. And it was a seminar given by the spokespeople of the Atlas and CMS experiment. There you can see Fabiola on the bottom right. She's now the Director General of CERN. And Joan Candela, he's actually a professor here in California at the University of Santa Barbara to do it. And just to point out, the one on the top left here is just reminding you that it was a really long time since people started thinking about the ideas of the LHC before they were actually able to really see the Higgs boson. People started in 1984, and this observation was in 2012. Of course, the theoretical ideas behind it, those came from the mid-1960s. So it was a really long period. And in fact, this discovery was awarded the Nobel Prize, and it went to the theorist who predicted the Higgs boson, Peter Higgs, who's up in Edinburgh, and Francois Englert as well. If you look on Wikipedia, you'll see there's a bit of a discussion about who exactly should be credited with the idea. I think what you can see there is the fact that a number of people came up with the same idea around the same time, actually independently, which is quite interesting to think about it. So we discovered Higgs. How many do we have? So far, we've actually made 17 million Higgs bosons at the LHC. Of course, we haven't actually managed to detect them all because we don't necessarily see all this data, but there's actually quite a lot that we've had so far. And what do we know about it? Well, we know a few things. We know its mass, which is something we had no idea about. There was no theoretical prediction here. It's about 125 GeV, and it's pretty heavy, about as heavy as a gold atom, which is pretty amazing if you think that this is really a fundamental particle. If you've heard about spin, maybe some of you heard about that. The Higgs boson is actually the only fundamental scalar particle, which means it has no spin. And we went and measured its p properties, things like its spin and parity. But then some of the questions that take a bit longer are, do we see exactly as many Higgs bosons as the standard model predicts? Which particles does it interact with? We need to really check that it actually interacts with all the different particles which have mass. So I'll say a bit more about the Higgs mass. It's actually a free parameter in the standard model. And what that means is that there is absolutely no theoretical prediction, but it's really important. It actually has a lot of impact on various different things. And so that's why we went and measured it. So you can see here, this looks similar to the plot that I showed you, but now we have a whole bunch more data, so we can do things more precisely. And here you can see how we actually do it. We collect the data, we make a prediction for the background, we do a fit, and from that, we really ask what is the mass of the Higgs boson. On the right, you can see a whole bunch of different measurements for the mass of the Higgs boson, using different channels, using different experiments, combining them all, where you can get to the combined value. And it's really simply asking the question, what is the position of this peak? Now, I always like to point this one out because people might ask me, can I blame the Higgs boson for being fat? I'm sorry to tell you the answer is no, because it actually turns out that if you calculate the mass of the 3 quarks inside the proton, this is only 0.2% of the total proton mass. So the rest of the mass actually comes from the gluons, which bind together the proton. That's the remaining 99.8%. So even though the Higgs boson is responsible for mass, it's only responsible for mass of elementary particles. So it's not the case that you can say I have, too many Higgs bosons hanging around. That's why I weigh too much. It doesn't work that way at all. I showed you this one before, but let me show you it again now, and we'll talk about it a little bit more. This is actually showing you the particle masses for various different particles, but actually what's on the y-axis is we measured the strength of the coupling of each of those particles to the Higgs boson. Because remember what I said is that the Higgs needs to couple more strongly to heavier particles. And so we can actually check this. And you can see the measurements that we've done, it looks like the Higgs is indeed really behaving exactly as we would expect in terms of the strength of the coupling. Now, to tell you something a little bit weird, I want you to kind of imagine that you're a goldfish in a gold tank, okay? And that's been your whole life. You've never been outside this tank. Would you necessarily be aware that you're in water? If you've never been outside, it's not obvious that you would to do it. And that's actually a very good analogy for the Higgs field. It actually turns out that the Higgs field is everywhere in the universe. And that's actually how we end up having this Higgs mechanism happening. But we don't necessarily notice it because, right, it's really everywhere and we can't really exit the universe. The Higgs boson is actually pretty narcissistic. The Higgs has to interact with all particles with mass. The Higgs boson has mass, and this was what it actually means, is that the Higgs boson must interact with itself. And so this is a loop. This is a way we sort of represent this, where you can actually see a Higgs boson going along, another Higgs boson that goes in the loop, and then interacts with itself. In fact, it's more than that. The Higgs boson interacts with itself actually without changing itself, which is one of the unusual things. Now, remember the shape of the Higgs potential that I showed you? In fact, the discovery of the Higgs boson doesn't tell us everything. We have a theory that predicts that shape, but we haven't been able to measure it. Indeed, what we've measured so far is the minimum of the potential. And so there are actually a whole bunch of different options that it could have if you go further away. And so this is obviously something that we really would like to check. Turns out it's actually pretty important because this relates to the fate of the universe. So this shows you a plot where you can see the Higgs mass on the x-axis, the mass of the top quark on the y-axis, and the dot is really where we are in terms of the measured values of these two parameters. Then you notice the colors. You can see in green, stability, in yellow, metastability, and in red, instability. And it turns out that with those current values, we're in this very interesting region. We're in the metastable region, or maybe we're in the stable region. We don't know. We need more accurate measurements to be sure to do it. But that's something, of course, we'd really like to know. Is this universe that we're in, is that actually stable? Just to say, before anyone gets worried, when we're in this region of metastability, that would mean that the universe, the lifetime of the universe would be extremely long. So it's unlikely to be something that would be relevant for our immediate lives. So that kind of brings me to the end. What I've been trying to show you is the fact that the Higgs boson really plays a central role in the Standard Model. But at the same time, we've only just met the Higgs particle. So there are many open questions, things we don't know the answers to. Things like, why does it have a mass of 125 GeV? What really is the shape of this Higgs potential? Is the universe stable? Is the Higgs boson the one in the Standard Model? Or is it something else? The good news is we've only had a small amount of data so far. And so we don't know. What else might we learn from the rest? Or maybe we even need more experiments to be able to answer these questions. Thank you.
Oh, brilliant. Thank you very much. So I'm now going to, let's see if I can do it. Now I'm going to ask you all to unmute yourselves now, please, and we'll try and go for a round of applause. I'll see if a few more people have unmuted. Come on, guys. All right.
I got a few. I'm doing some imagining.
So I think we have a bit of time for questions. So feel free to unmute yourselves and ask any, or pop it in the chat, and we can read out. Oh, here you go. Question from Oliver about what do we mean by metastability versus stability?
So what stability would mean, and so what we're actually talking about here is that due to the shape of the Higgs potential, the universe could decay because it's unstable. Okay, so that's the exact thing we're talking about here. And so if it's stable, that would mean that this would never happen in the universe. What metastable means is that it's not quite stable, but it would take a really long time. And so that's what metastable means. And that's why I was saying it's not something we should be too concerned about, because even if we are there, it's unlikely to happen anytime soon.
We've got another question as well. So how did we know in which decays we'd expect to find the Higgs boson?
So it's because, actually, let me show you this plot again, this one here. So you notice that there are actually labels on the left, on the y-axis, where it says MF K kappa F over V, okay? What matters there is the MF and the kappa F to do it, is essentially we can actually predict that for all particles, and F actually here stands for fermions, this is just a group of particles, including the quarks. And what it's actually saying is that we can calculate those values from the Standard Model. And in fact, if you assume the Standard Model kappa is 1, so you're saying that the Standard Model says that if I have a particle, I should take its mass, I should divide by V, which is actually the vacuum expectation value. And so it's as simple as you take the standard model, you do a calculation, and it actually behaves this formula. So that was for one set of particles. The plot is actually cheating a tiny bit. It's showing two types of particles. So there's a slightly different formula for the other ones, but it's essentially the same argument that we can really make it linearly depend on the particle mass, which is something you can calculate using field theory from the standard model.
Awesome. I've got a question now as well. So the Higgs boson gives all the elementary particles their mass, and it's about the neutrinos. So does that they have a very, very small mass, most likely. So do they interact with the Higgs, or is it something else?
We don't know, actually. So that's, it again comes back to one of those unsolved questions in particle physics. It might be that they get their mass from the Higgs boson, but there are also some other pretty cool theories that could give neutrinos masses in other ways. And so there are a number of different experiments that are ongoing now, trying to figure out, what actually is these masses, because we only sort of know relative masses so far. We haven't yet measured the absolute scale, and to try and see which of those theories might be correct, because they predict some other things as well.
So is it sort of, we're not sure if they get it from the Higgs because we've not seen like a Higgs neutrino decay, or is there something in the standard model which, like, are they kind of not really included in the standard model Higgs interaction bit, or is it just that we've not seen any?
So this is an interesting point. Different people will give you different answers. So in the original conception of the standard model, they would actually have no mass at all to do it, right? So that's what we originally had. But then once we figured out that they did have mass, it was a small modification to the standard model that was needed to change. So I guess the answer is they can be accommodated in the standard model, but at the same time, they don't have to be. We are very, very unlikely to ever see a Higgs to neutrino decay, because from this plot that I'm showing you, right, the neutrino masses are tiny. So what that means is that the interaction strength of a neutrino with a Higgs is going to be tiny, which means it would happen really rarely. So there's like absolutely no chance that we would ever be able to directly observe that one from like making Higgs bosons looking for the decay to neutrinos. I think we'd have to run the LHC for the age of the universe, or maybe even longer.
That's quite a lot of time.
Got one in the chat. Oh, okay. My screen's frozen.
Oh, yeah, I see it. So out of all the beautiful places you've worked or studied at, which you showed at the beginning, which one's your favorite?
Oh gosh, do I have to choose?
We'll edit it out of the recording, so no one will be offended.
I think truthfully, that's an incredibly hard question to answer. I actually really enjoy, because I get to go to all those places still to do it. I mean, CERN is a fantastic place, right? Because there we do this particle physics like nowhere else on Earth. And so you get all these people who are all excited about doing particle physics. So from a work perspective, that's a lot of fun. But being in Berkeley is great too. I have fantastic students that I get to work with. The weather's mostly nice here, except when there are fires. And then, of course, in Cape Town, I still have my family. And Cape Town, I think, is still the most beautiful city in the world. So I think I like things about all of them, is the answer I'm going to give here. I'm not going to choose.
Very diplomatic. That kind of leads me on to a question I had about, is there kind of a difference in research culture between research in the US, or working in US laboratories, or working in say at CERN European laboratories, or is there any kind of trend based on that?
I think, well, so on the one hand, right, these collaborations are extremely international. So even when I was at CERN, I was working with people from every country around the world to do it. So even being at CERN, right, I would see so many different cultures, and that's one of the fun things, is seeing how different everybody is. I would say that Europeans versus Americans, there are some differences. I mean, some things are to do with sort of the cultural expectations about how long you work, how much you take holidays, this sort of thing. So that's different for sure. But otherwise, even here, I think if I look at the group, the ACTIS group here in Berkeley, I think maybe 90% of us come from different countries. So you get the same people basically when you go to different places, is a bit how it works.
Oh, very nice, very nice. We've also, I don't know if you can see the chat, we've got a comment just saying that we really enjoyed the slide titles. So
thank you.
So
any other questions? I can't quite see the chat, I'm afraid.
Yeah, no worries. There's a couple. I'll read them out. So what is the field theory behind the standard model? So the person asking understands that the group theory comes into it, but what would you say are the most relevant fields of mathematics behind particle physics?
So group theory is indeed the root of it. So the standard model is an SU3 cross SU2 cross U1 group theory. That's actually the groups that we need to describe the various different interactions. I think that is a key starting point. But then after that, it really does need to be an actual field theory course. So, you know, when I was joking and saying the mathematics is very simple for the Higgs, that really relies on being able to do the field theoretical calculations for the Higgs boson. And if you're able to do that, then you'd be able to answer mathematically these things I've been saying. For example, you know, what is the rate of the decay of the Higgs to particles? How often do we produce the Higgs? That's what field theory would actually teach you. So I think as soon as you get to that stage, it's more about physics necessarily than mathematics to do it, because probably those of you who've taken a few physics courses notice that we do things a little bit differently in physics compared to mathematics. So at some point, those two fields kind of branch off and they go their different ways, as I would say.
I've also got a question asking, how do we exactly know that the signal peak corresponds to the Higgs rather than just another particle with a mass of 125 GeV?
So indeed, we did not know that at the beginning. And so if you look very carefully when we announced the discoveries, we did not say we found the Higgs boson. I think we said we found a new scalar or a new particle to do it. But the way we do that, right, is we take these theories, we do our calculations, and we compare them to our predictions. So for example, we checked what was the spin of the Higgs boson. Once that actually told us the spin, we said, it can't be this, this, and this particle. Then we checked its parity. Again, another prediction. It was the same. Then finally, we actually measured, you know, all these interactions, and we checked their rates, and we compare them to the theory. And with each of those comparisons, when it actually agrees numerically with the prediction, this gives us increasing confidence. So I think it took us maybe a year or so where we started saying Higgs-like, and then finally we said Higgs boson. But indeed, experimentalists, we were very cautious about claiming too soon that it was necessarily the Higgs boson. I'll tell you one sort of anecdote. There was a sort of, it's called the mass crisis. So in Atlas, when we actually measured our Higgs to photons and our Higgs to 4 electron channels with more data, we actually noticed that the mass looked a little bit different between the two of them. And so we were wondering, you know, is this two particles? You know, are there two particles going on here, or, you know, slightly shifted, or is there something going on in the detector, or is it just a statistical fluctuation because statistics are low? So we spent about a year doing very, very careful cross checks. We learned a huge amount about our detector, but actually the answer ended up being it was just a statistical fluctuation. There's just one particle going on. But indeed, you've got to be skeptical and curious when you see something and not just assume it's exactly what you're looking.
Yeah. There's a question there in the chat that leads quite nicely from that. So how confident were you when you first saw the data that it actually was the Higgs? I imagine people probably got quite excited at the start.
Well, so I'll tell you, my story is I knew, of course, what was going on inside Atlas, right? So we had like an 8-hour meeting where we kind of reviewed our results and things. So we'd, you know, discussed it, we'd all ask questions, everything like that. And I knew there were rumors that CMS was excited, right? You can't hide excitement. But I didn't know all the details of what was going on in CMS. So it was actually when I watched that seminar, and I think that's why I like to show it, when they actually showed the CMS results, they showed that they were seeing exactly the same thing as Atlas, done independently, right? Then I said, hey, hold on, that has to be real to do it. I don't think I had any doubts it was a Higgs. I mean, I think it's cool and fun and important to check it, but I would have been more confident of that. But I think it was really having those two independent experiments. For me, that was a very important step.
I've got a question as well, actually. So it's been like a lot of news lately on Fermilab's Muon G-2 experiment. I'm sure you've been following, yeah, especially at Manchester, because we're quite heavily involved. We just had a seminar a couple of weeks ago about it, actually. What was I going to say? Yeah, no, what I was going to say was, do you think the results from this, especially if they get confirmed with the sort of 5 sigma, hallmark, could have any effects on the sort of Higgs research you've been doing? Because, adjustments might need to be made for the standard model.
Also, I think any indication on the standard model not working would be fantastic, right? And I don't mind if it comes from G-2, if it comes from, any experiment, that would be fantastic, because the point is we have this model, right? And we're trying to look for cracks in it. And we can look in every single way, and it doesn't matter which way, we just need to find a crack. And then that would actually force us to really evaluate what's going on to do it. For G-2, it's a bit too early to tell. And indeed some of the more interesting parts are these different theoretical predictions, because there are actually a couple theoretical predictions which are quite different. And they actually really make a big difference in how significant that is. So we're all watching that very eagerly. It's very interesting. But there's going to be some time. We need people to do some work to figure out what we should be expecting. But it's very interesting.
Okay, thank you. We've got another one, actually. Talking about lepton university experiment.
Yep. That would be the other one that people are, this is exactly the other one that we're keeping an eager eye on to see what happens. Again, we don't know.
Can I just ask as well, actually, what you sort of particularly mean by a scalar particle?
Sure.
Yeah.
I didn't explain that. No, I didn't explain it at all. No, so what it is elementary particles have a whole bunch of different properties, right? So the one that's easy to explain is the mass. To do it. They can also have charge. They also have things like color. There's a whole bunch. One of these is spin, okay? And there you can have particles being right-handed or left-handed particles. So we think about it really like a little top spinning, but it's not. It's just a property to do it. And so particles have various different quantum units of spin. So for example, they can have 0, they can have 1, they can have 2, etc. And then the parity comes in. It can be positive or negative parity, which is about how that spin actually behaves in a reflection in a mirror to do it. Now the Higgs boson is weird because it has no spin. So it's just 0, basically, to have it.
And that makes it a scalar particle, does it?
Yeah, scalar just means spin 0. It's just another word for it. It's the same thing.
Kind of like to think about it as like a tensor rank. So like a rank 0 tensor is a scalar. So a spin 0 particle is a scalar particle. That's how I like to think of it. Really.
Oh, okay.
For
I've
those
not
who
come across tensors yet.
For those who did advanced dynamics, you know what we're talking about. So yeah.
We need a postulus on this.
Yeah. Right. I think you've probably got time for maybe one more question if anyone has one. There's another one in the chat. So would there be any value in installing some sort of neutrino detector at the LHC, like a super K, if that's even realistically possible?
So that's actually something I wondered about, but in fact, we actually have a new detector at the LHC which does detect neutrinos, but it's not like super K, it's completely different. It's something called phaser, F-A-S-E-R, and it's actually basically really, really far away along the beamline. And so it just does some small fraction of them to do it. And so that one actually does detect neutrinos, and they had some recent results showing a little bit what they could actually see. However, the problem would be like something like literally like super K, we have these events which actually protons collide 40 million times a second. The trouble would be is that we produce neutrinos in every single event. So we don't have a technology where we'd be able to figure out, to read it out in the rate that we need to do. And so you would be able to see neutrinos, you just see lots and lots of neutrinos. The problem would be you wouldn't be able to associate them to the events to do it. So yes, it would be interesting. We don't have a way to be able to do that with current technologies, but doesn't mean we wouldn't be able to for the future.
That'd be very exciting. Huh? Okay, well, I think that's probably it for questions. So yeah, thank you so much for joining us, Heather, and thank you so much for everyone who came.
Yep, lovely to meet you all kind of virtually, and good luck for the exam.
Thank you.
Bye.
Bye-bye. Bye-bye.